structures today, and we're going to go the direction of, we got to hit some dot structures, and we need to talk a little bit about certain type of dot structure. I'll talk about that when we get there. And then we're hoping to get through part of the shapes of molecules like trigonoplanar and linear, tetrahedral, those things. We won't be able to finish shapes today. That's what my plan is tomorrow, to finish shapes, get into some polar bonds, polarity, molecular attractions. We really don't have a whole lot of time left. We're down now to, gosh, it seems like we have a lot of days there where quizzes Friday the next week we get back, but we really only have one day that week for a lecture day, because 2 days we're off and 1 day is a review quiz day. So yeah, we don't have a whole lot of days. And we didn't want to have the quiz the next week because that's when the M-step testing is, and so there's all that M-step testing. So yeah, we think it would be best to just get this quiz out of the way. Okay, now we were here yesterday. I asked you to write down some guidelines for writing dot structures. We're going to be doing lots and lots of dot structures, so you'll get real good at those, and they won't be difficult at all. You'll run into some strange things, though, and number 5 is just one of a few strange things that would happen. Sometimes you'll have more electrons than you should have. You've got to get rid of some of your electrons in your structure by making double or triple bonds. And I know that you've done that before. There's other weird things, though, that'll come up. Now, did we get here yesterday? Did we do the dot structure for SEF2? Okay, that's where we finished. Okay. The steps that I gave you yesterday, I want you to do these every dot structure that you do. Start with counting the number of electrons, then identify which one goes in the middle, and then put the other peripheral atoms around with single bonds, then add the electrons. Do that every time. And then you won't ever have any trouble because you'll be doing the same thing. And there won't be any difficult ones. So
Please pardon this interruption. This is the last call for any juniors who have not yet done their pre-bubbling. There are about 30 students. The names are Anna Stiani.
Oh, you're not going to read 30 names. She's a bred.
Jared Lipinski, Monty Rokolov, Emily Laura, Zach McCarty, Justin McDonald, Noah Riddle, Daniel Schweizer.
Because we don't want to take it, that's why they don't want to bubble it.
Joe Horseman, Brittany Zora, and the 3 seniors, Henry Klein, Sharon Shockey, and
Oh, don't say their names.
have not already done so. Please report to the lecturer.
All right. So we're doing the same thing here. SE, now you'll want to have a periodic table handy. If you can't see that one, then if you can grab one out. The lights? Okay. Sure. Is that better? How many valence electrons does SE have? Valence electrons are the outermost S and P electrons. It's got 6, that's right. It's got 2 electrons in the S. It's in the 4th row, so it's got 4s2, and then over there 4p4. So it's got 6 electrons. How many does fluorine have? 7. And there's 2 fluorines, so it's going to be 7 times 2. So the fluorines are going to contribute 14 electrons. The selenium is going to contribute another 6. So that's a total of 20 electrons that we're going to have to account for in the dot structure of SEF2. So what we'll do is determine which one is the least electronegative. And so typically, it's going to be the one that's written first in the formula. Rarely is the one in the middle not the first one. So SE, sure enough, does go in the middle. We know that because fluorine is the highest electronegativity. You don't have to put fluorine in the middle. Step number 3 is give a single bond to the peripheral atoms, at least right now. That may change.
Wait, what's a valence electron?
The outermost electron, the outermost energy level.
Okay.
So after the noble gas core. Not including D's, though, it's just S and P's.
Okay.
All right. So the step number 4 is now that we have some semblance of a structure, we need to account for all the electrons. So go ahead and put lone pairs of electrons around all the atoms so that they all have 8 electrons attached to them. So the octet rule is still the guiding principle. We're going to find there are some exceptions to the octet rule. In fact, there's a number of exceptions. But that's still what we're always going to fall back to. Simon?
Does that one have to be like a bent shape?
It is bent. How do you know?
Because like, I forgot what it was, but like there's like the right side's like more positive, the left side's negative. So I don't know, but like that's why chem logic.
Yeah, you're mixing two different concepts together into the same thing, and that's you're part right. Yes, it's bent, but for the wrong reason.
Yeah, the reason I forgot.
You're looking at polarity, whether it's a polar molecule, and so yeah, we'll talk about the shapes in a few minutes. Anyway, now once you have 8 electrons around everybody, now we have to count up how many electrons are represented in the structure. 2, 4, 6, 8, those lines are 2 electrons, 10, 12, 14, 16, 18, 20. Oh, how nice. The number of electrons that I have represented here equals the number of electrons that the SE and the Fs contribute. So we'll think that this is the correct dot structure for SEF2. If everybody has 8 electrons, and you have the total number of electrons in your structure as there should be, then we assume that it's correct. And moving on. The next compound to do the dot structure for is carbon dioxide. Carbon dioxide, we're going to go through the exact same sequence of reasoning. The carbon, how many valence electrons? 4. Got 4. Oxygen? 6, and there are 2 oxygens. So there's going to be a total of 4 plus 12 is 16 electrons that we need to account for in CO2. That's step 1, is determine the number of electrons that you have to worry about. Step number 2 is identify which one is going to go in the middle. It's the first one written in the formula, and the oxygen is the second highest in electronegativity. Don't count on oxygen going in the middle, except for weird cases like when you don't have a choice. Water, hydrogen peroxide, then it has to go in the middle. So then we're going to take the central atom and connect the peripheral atoms to it, first with a single bond. That can change, we may need a double bond, we will here. But at first we're just going to add single bonds, and then add enough electrons in to give everybody 8 electrons. That's step 4. Just go ahead and put lone pairs around everything to get 8 electrons around all atoms. Now we're going to count and see how do our number of electrons here relate to the number of electrons here. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I've got 20 electrons in my structure, but I should only have 16. The carbon and the 2 oxygens add up to 16 electrons. I can only have 16 in my structure. So what do I do to get rid of some electrons? Well, I have to make double bond. Right. So to make a double bond, what we're going to do is the carbon and oxygen, rather than having carbon's own pairs of electrons and oxygen's own pair of electrons there, we're just going to go ahead and erase those. And rather than them having their own pair of electrons, they'll share a pair of electrons. So I erased 4, but then added back in 2. So then that change was I lost 2 electrons. Got rid of 2 electrons. Well, that would take us down to 18. I need 16. So I have a choice. I can either make a double bond over there or make that a triple bond. Is one more correct than the other one? No, you can do either one. Typically, we'll kind of balance it out and put a second double bond in here with that oxygen. It looks like that. Don't forget, when you make a second bond, you need to erase one from each of the atoms. Okay? 2, 4, 6, 8, 10, 12, 14, 16. So I've got 16 electrons in there. Matches up with the 16 that I should have. That's the dot structure of CO2. We okay with that? Let me know if you have any questions. I'm going to keep zipping through a bunch of examples. Yeah?
Trying to
the valence electron. This number over here?
Yeah.
So carbon has, it's in the second row. The valence shell would be the second energy level. There's 2 s electrons and 2 p electrons, for a total of 4 valence electrons.
Like, yeah. I know the word for C and O, but for S, like, I'm kind of confused.
Now the SE is in the 4th row. There's 4s2, and then we skip over the d's because the d's don't count for valence electrons, just s's and p's. So there's 4s2, and then over to the 4p4. So 2 plus 4. That's how I came up with the 6.
Oh, I actually looked at the SC and SE.
Oh, yeah, and from there it's hard to see. Yeah, because the C does look like an E. Yeah, selenium number 34. Yes?
So you don't count D and F?
No, don't count the D's, don't count the F's for valence. Okay. Next one is going to be ClO4 with a -1. And so in this case we have a polyatomic ion, the perchlorate ion. It turns out that polyatomic ions are held together with covalent bonds. So what do we do about this? Chlorine, how many valence electrons? 7, right? Oxygen has 6, and there are 4 oxygens. And then what do we do about that -1? This adds another electron. Somebody said subtract. Did you submit?
Yeah.
Okay.
Because it's bonded stuff.
Yeah. Okay. You're allowed to make that mistake one time, but that's it. So how many electrons? 7 plus 24 is 31, plus another one is 32. Who goes in the middle? Yeah, oxygen doesn't go in the middle, so it makes it easy to decide who does. Chlorine. This is kind of weird too, because chlorine's got a pretty high electronegativity, but compared to oxygen, it's low. So the number 3 step is we're going to put single bonds to all the oxygens, and then add the lone pairs to get everybody 8 electrons. The Cl already has 8 electrons around it with the 4 bonds that it's made. And it looks like that. And if we count the number of electrons, 2, 4, 6, 8, starting on the left, 10, 12, 14, 16, 18, 20, 22, 24, 26, 30. Oh, geez,
26,
what did I do?
26, 28, 30, 32.
I skipped over 28, didn't I?
You just said 26.
Okay, so this, the left, top, and right oxygen, that's 24 electrons. 26, 28, 30, 36. I needed a do-over. Okay, so we've got 32 electrons in this thing. Sorry. And that is the same and matches up with the 32 electrons I
They're
should
going to see the video.
Yeah. If that's the worst thing that I do. I'll
Listing
be
of
fine.
names in the video too. So.
What else?
There's a listing of names in the video too. So.
Oh, yeah.
Oh, yeah, that's right. That's right. Should turn that off.
It's just a link.
I'm not going to go crazy if you don't do this, but when you have a polyatomic ion, we should make this look different from this because that's a neutral molecule. Yeah, right, exactly. Put brackets around polyatomic ions and indicate what the charge is on the outside like that. Again, I'm not going to mark you down and take points off if you forget or don't do this, but this is something that's more complete, is to indicate when you have a polyatomic ion or something charged. Okay, we're moving. Now here's something different. Sulfur hexafluoride. We're going to try to do the dot structure of sulfur hexafluoride. Let's count. Sulfur, 6 electrons. Fluorine has 7, and there are 6 fluorines. Gosh, I thought there were a lot of electrons last time. So we're going to deal with 48 electrons here, 6 plus 42. Who goes in the middle? The sulfur's got to go in the middle. All right, now we're going to have to put 6 fluorines on here. See, well, fluorine is only, fluorine's kind of like hydrogen, it only makes 1 bond.
But you add it to the other fluorine. You attach 4 and then.
No, it has
But then one of those 4 that are attached to sulfur is going to have to make another bond.